To continue from last time, remember that that our goal for the day is to show that several natural problems and graph problems mostly are going to be NP complete. In particular, we're going to start with the Clique problem. We're going to reduce 3CNF to the Clique problem. But remember this is our landscape. And so visually what we're doing is we're taking problems in NP and we're reducing them down to an NP complete problem, right? And we needed a starting point. Remember that starting point was this language called L sub NP, which is the canonically complete language for that complexity class, where it just encodes a machine and an input, and it accepts if that machine accepts x in a polynomial number of steps. Stephen Cook showed that you can actually reduce this down to the satisfiability problem. Right now, I'm going to run out of room, but that's okay. And then I didn't show it, but certainly it's possible to show that you can actually take SAT and reformulate it as a 3CNF problem. Remember, that's conjunctive normal form, where you've got a bunch of clauses with at most 3 variables that are the disjunction of those 3 variables or their negation. And then all the clauses are taken as a conjunction together, a bunch of ands, right? So what we're going to do, and sorry, I'll extend my landscape up here to include NP complete. What we're going to do today is we're going to reduce it further up to Clique. All right? Now, why is it enough to show that you can reduce one problem to another problem? Remember the definition of NP complete. Everything in NP is going to reduce to this over here, including any other NP complete problem, right? All this stuff reduces to NP complete problems by definition. And by transitivity, L sub NP reduces to 3CNF. And what we're going to show is 3CNF reduces to Clique. Therefore, by transitivity, everything in NP reduces to Clique. If you were able to show the other way, say that you were able to show that Clique reduces back down to something over here in P, well, then that would collapse this entire landscape. Because you could apply that problem that operates in polynomial time to solve the Clique problem. Well, once you've solved the Clique problem, then you've solved every other problem in this entire class. Right? You've solved an infinite number of problems with just one algorithm. Right? That's probably why it's not likely to happen. Okay? But this is where we're going to focus on today, and then we're going to reduce it further to yet another problem up here. Okay? So to remind ourselves, there's a 5-step process. I think that this 5-step process, I'll attribute it to Gary and Johnson. Gary and Johnson, it's a book, quite old now, maybe 20, 30 years or so, I forget when. But it's just a compendium of NP complete problems. They compiled this list, when this idea first came out, of course, everybody rushed to show this is NP complete and this is NP complete. Here's a reduction, here's a reduction. It's not so much cutting edge research anymore, but they instead it's kind of a standard thing. If you're going to show that this is a difficult problem, it's you just show a reduction. Gary and Johnson is a nice compendium of problems because it's got a nice breadth of problems that you can go ahead and check out and, hey, that looks very similar to my problem. Maybe there's a reduction from that problem over to this problem. And so it's a nice book that has 100 or so just NP complete problems. And in that book, I think if memory serves, is the following 5-step process. First, you need to show that your problem that you want to show is NP complete is in NP. Right? Remember, the definition of NP completeness is that it has to be in the class, and also every other problem reduces to it. Okay? So the first step, of course, would be to fulfill the first part of that definition. Second, you again, this is why Gary and Johnson is a useful tool, because you have to find a known NP complete problem to reduce from. Select a known NP complete problem to reduce from, right, to your problem that you want to show as NP complete. 3, you come up with you develop a mapping. Let me go ahead and give these names. You select a known NP complete problem, we'll call it A, to your problem B. Right? In other words, you want to show that A is polynomial time reducible to B. Develop a mapping such that you map yes instances of A to yes instances of B. Right? Now, with respect to 3CNF, which is a Boolean formula, right, we're going to map Boolean formulas to Clique. The Clique problem is a bunch of graphs. So we're going to map a Boolean formula to a graph that preserves these instances. And by exclusion, no instances of A map to no instances of B. 4, prove your mapping preserves solutions. Right? So coming up with it basically also informs the proof, and so these go hand in hand. A lot of it is going to be a proof by construction. That's just how it works, right? And then 5, show that your mapping is polytime computable. That is that this mapping up here that you developed can be computed by a deterministic polynomial time Turing machine. Now, the reason that you want to show this is so that you don't cheat, right? Here's a cheating reduction. Take a satisfiability problem, right, and then spend an exponential amount of time to actually solve it. Come up with a yes or a no. And if the answer is yes, output one variable, right? And now it's trivially solvable. Just set that variable to true. If it's no, output a contradiction. Now it's trivially, not solvable because there's no value that can make it true, right? Now you're cheating by using the power of the reduction in order to answer the original question, rather than just mapping instances to instances. You want to make sure that your mapping is no more powerful than the complexity classes that you are comparing everything with. So you don't want to give the reduction itself an exponential amount of power. You want to make sure that it is only it's at most a polynomial time reduction. There are other notions of reductions, by the way. There are truth table reductions, or there are logarithmic space reductions, right? Basically, you can have an even more fine-grained approach to your complexity theory, where you say, well, under a certain type of reduction, it's complete, but under a different type of reduction, it's not complete. You can't even reduce it from this problem to this problem if you restrict the type of reduction that you do. You can ask questions like that. But that's going to be our map. That's if you really want to get into complexity theory. This is our roadmap for how we're going to show that 3CNF is polynomial time reducible to the Clique problem. At this point, let's go ahead and go back to yesterday to remind ourselves what the Clique problem is. Given a graph G and an integer k, does there exist a subset of vertices that form a clique? A clique is simply just a collection of vertices that are all connected, right? So basically a complete subgraph. This is a clique of size 3 over here in red. This is a clique of size 4 over here in red. And there's no clique of size 5, 6, 7, 8, etc. There's always a clique of size 2, right? As long as there is an edge. But this is why we call them cliques, right? What's a clique? If a group of people are cliquey, right? They're very tightly knit, right? They all know each other. And then other people may not, all four of these friends are in common. They're all friends with each other. But this friend is not a friend with anybody else over here. But the connection between these two groups is this person and this person or whatever. They know each other, right? And then there's this other person out here that only knows those two people, right? So that's the idea of a clique. We're wanting to find a highly connected subgraph in the clique problem, okay? So our first step is to show that the problem we want to reduce to, or show that it's NP complete, show that clique is in NP, okay? All that requires us to do is to come up with a non-deterministic algorithm that operates in polynomial time. Remember, non-determinism means that you've got a guess phase and a verification phase. So what are we going to be guessing here? We're simply going to be guessing a subset of size k, right? So guess a subset C of vertices of size k. That's the first step, right? And since this is at most k, well then this is order n to the k, right? Or order k if you want to, there. Right? It's you're just which is at most order n. Right? You're doing non-determinism here because you're guessing, but you're only guessing how many things? Well, at most v, and there are at most n vertices. Okay. B, verify. That is, given C, which is a subset of vertices, is it a clique? Right? We already, by guessing it as a proper size, we don't need to check that its size is also correct. Just given this subset here, verify. So for each pair of vertices, x, y, in that supposed clique, if x, y is not an edge, then does it form a clique? Nope, so reject. Otherwise, if every pair has an edge between them, then you accept. Now this entire thing accepts if and only if at least one subset C is a clique. So therefore, clique is in NP. Okay? All you have to do is develop an algorithm for it. Right? And it's simple enough. It's just that you got to wrap your head around the idea of non-determinism. It's magic, and that's just what you have to accept. It's not a real computational model. It's not something that can actually be built or realized in the real world. It can be simulated at a cost of exponential blow-up of time, but that's not what we're trying to do here. And of course, this is going to be k, choose 2, which is at most order n squared. So this operates in polynomial time, this operates in polynomial time, and so that takes care of the p of NP, and of course this guess phase, that's the non-determinism part. Right? If we didn't have this non-determinism part, well then it would just be p. That's step 1. Step 2. We need to select a known NP complete problem to reduce from. That's already done for us. 3CNF. Right? We're going to show that 3CNF reduces to clique. Okay? 3. We need to come up with a mapping. So develop a mapping. Right? The idea here, now, I'm not going to leave you to your own devices and to come up with this on your own. That would be a CS4, 423 topic. Right? Here's the problem. Go ahead and develop your own gadget. What we're going to do is we're going to map formulas to a graph. Right? And these are generally called gadgets. Gadgets. Right? They're called graph gadgets. And what that means is simply that I'm going to come up with this graph that has these certain properties that then maps those properties back to the original. But we're going to have a, we're going to have a 3CNF formula, and we're going to encode that formula inside of a graph. Okay? Now that's not that big. That's not that weird, right? Think about what a formula is. A formula. What's another way of thinking about a formula? If I've got the following formula, let's go ahead and take a look at an example here. X1 or not X2 or X3. And X1 or not X2 or not X3. And X1 or X2 or X3. All right? What's another way of drawing this formula? Nobody's been raising their hand when I've asked if you've had 230 or 231 yet. Right? Okay. X1, what do I want? X2 and X3. Right? Those are going to be inputs to a circuit. Let's go ahead and take care of this first clause here. This first clause is going to be, well, X1 and X3, 2. How do you negate a circuit? Honestly, I don't remember. I think it's going to be this. Is that right? Okay, thank you. EE, you're going to help me here, right? Because I don't remember all my circuit stuff, right? So what is this? This is an OR. What's an OR gate look like? I think that. Yes, thank you. Good. All right, I'm passing my circuit exam right now. All right. All right. And then you could do the same thing with this one and this one. Let's go ahead and we can have cross wires here, right? We can take negation of X3. So I'll go ahead and feed that into another negation circuit. And then I will feed in the original, let's see, this one, and this one into this OR gate right here. And then I'll go ahead and leave off the last clause here, but then I'll go ahead and take these together. Oops, I don't want to do it that way. There we go. I saved myself. Oh, thank you. Okay, I did not pass my circuit exam here. There we go. And now an AND gate looks like what I had before. Okay, there we go. There's the first two circuits. If I just ignored the last clause here, there it is. What is that thing right there? Of course, it's a circuit. Huh? But what else? How did I draw it? What does it look like? Looks like a graph to me, right? So all these connections that you should be drawing, coming up with in your head, and like, oh, you know what? Why do we study graphs? Because anything can be modeled by a graph. Why do we study binary? Because anything can be encoded as binary. Right? When you get down to the nitty-gritty, low-level stuff, everything ends up being the same. You can take a graph and model it as a circuit. A circuit can be modeled as a graph, or it can be modeled as a formula. So this mapping is not all that surprising, because a circuit is a graph, or it can be modeled as one at least. So, and what we're going to do is we're going to map this formula to not this graph in particular, but to a different type of graph, such that this formula is satisfiable if and only if this graph over here has a clique of size k. Right? So the formula is satisfiable if and only if, this is our goal, the graph has a clique of size k. Okay? That's what we're going to do. So here it is. Here's our mapping. Okay? Let phi be our CNF formula. C1 and C2 and ... and CK be a 3CNF formula. Okay? Each one of these things, remember, is a clause. with 3 variables or their negation, right? And so we've got n variables in general, x1 through xn, okay? That's going to be our 3C and F formula. Then what we're going to do is we're going to create a graph. Create a graph. Its variables, let's see, it's going to have 3k variables. All right? Or not variables. 3k vertices. Each one for each variable in each clause. So why do I have 3k of them? Because there are k clauses, 3 variables each, so I'm going to have 3k, 3 times k the vertices in my graph. Right? What about edges? Edges will be drawn as follows. Right? Let's say that, let's see, or you know what, sorry, let me give you labels first. Labels for the vertices. For a clause CI, let's say that it is V1 or X1, X2, and X3, or, right? And then I'll label them, I'll put a superscript on the top as well to show that these are in the ith clause. What we're going to do is we're going to produce vertices called V1I, V2I, and V3I. Okay? 3 vertices. I drew that one kind of small. Okay? And then the edges. We will go ahead and connect V alpha to the I and V beta to the J will be an edge if and only if both of the following conditions hold. Right? 1, vertices are from different clauses. That is, V, whatever it is, alpha or I is not equal to J. Right? They're not from the same clause. Because remember, for the ith clause, I put a superscript above them all to make sure that they are to label them all as being in the same clause. And 2, the variables are consistent. What does consistency mean? It just means that V alpha I is not the negation of V B to the J. Right? So as long as they're not negations of each other. Now don't worry about this, because what I'm going to do is I'm going to go ahead and go back to this example, and let's actually generate a graph according to these rules. Okay? So I've got 1, 2, 3 clauses, so I will end up having 3 times 3, 9 vertices. I'm going to draw them like this. Right? So I'm going to draw it so that clause 1 is over here, clause 2 is over here, and clause 3 is over here. Each one of them has a variable, V1, or it's going to end up being V1, 1, V2, 1, but it's going to correspond to the negation. So let me go ahead and draw it like this. X1, X2 negation, and X3, like this. Right? X1, the negation of X2, and X3. Over here, I'll have 3 other vertices. And over here, I'll have 3 more vertices. For C2, this is C2, and this is C3, C1 over here. X1, negation of X2, negation. All right, sorry about that. Batteries ran out. Okay, so that corresponds to x1, negation of x2, negation of x3. The last one just has all the variables and no negations, x2 and x3. Okay, that corresponds to these 9 vertices here. Now remember, we're going to draw edges if the vertices are in different clauses. So in other words, within this clause, I'm not going to draw any edges whatsoever. Within this clause, no edges. Within this clause, no edges. Between the clauses, I will start to draw edges. Okay? That's the first condition, that I is not equal to j. Now, the second condition is that the variables are not are consistent, that one is not the negation of the other. Okay? So let's go ahead and start over here, and for this, switch to a thinner pen. Here we go. x1. Now I need to know whether or not I should connect it to this one, and or this one. Are these the negation of each other? Nope. So go ahead and draw it. And of course, neither one of these are the negation of each other. Okay. Now, not x2. That's going to be consistent with all 3 variables. Remember, this is negation of x2, but that's consistent. Okay. x3. Well, that's going to go to x1 and the negation of x2. But now what about these two right here? Sorry. Negation of x3 and x3. Are those consistent? No. So I end up not drawing that edge. Okay? That took care of all 3 of these. Now I need to take care of these 3 with respect to over here. And so x1 and x1, that's consistent, consistent, and consistent. Negation of x2, of course, that's consistent with the first. What about these 2, though? Negation of x2 and x2, those are inconsistent. They're the negations of each other. So I don't draw those. And finally, x3 goes to x1 and x2, but not to x3 because this is the negation of that one. Right? I did this clause with respect to this clause with respect to this clause. I still need one more. This clause with respect to this clause. So x1 goes to all 3. x2 goes to x1, but not to x2 because negation of x2 does not go to x2 because they're inconsistent. And this is 3 down here, by the way. x3 goes to all 3 of them, and x3 is consistent with itself. Okay? Now, let's go back to the example over here. Okay? Is this satisfiable? Can you come up with an assignment that makes this satisfiable? Well, we could do the brute force truth table, right? x1, x2, x3, 0, 0, 0, 0, 0, 1, dot, dot, dot. And there will be 8 possibilities. What about this one? False, true, false. Right? False under this first one. True, true. So that works. False, false, false. So does this work? Does that satisfy it? No. Okay. Same idea here. That last one will be true. That takes care of the first clause. That one will be false. So that takes care of that clause. And this also takes care of this clause, right? There are several others that will satisfy this. So this does satisfy it. What does that correspond to over here in this graph? Right? What about x1, x2, and x3 being 0, 0, 1? What does that correspond to over here? Anybody see it? So what are we looking for? We're looking for a clique of size what? 1, 2, 3 clauses. We're looking for a clique of size 3. Does this correspond to a clique of size 3 somewhere in here? Where?
In C1, x3.
Okay, you set it equal to true, and what do you do with it?
It's connected to the x2 in C3 and the x1 in
x1 and C2 connected. You want to do this one right here. Okay. And I would need these two to be connected. And are they? Why? Because they're consistent with each other. And they're in different clauses. This is not the only one, by the way. And I'm not sure that that even does that really even correspond to this particular one. I don't know. I'd have to think about that interpretation for a second. But that's certainly a clique of size 3. There are several cliques of size 3 here, right? That's our mapping. What we need to do is we need to prove. So step 3 or step 4, we need to prove the mapping preserves solutions. Okay? Now I'm not going to be too formal about this. This is only CS3 course, but I need a better pen. But the idea is basically by the construction, right? Suppose phi is satisfiable, right? If phi is satisfiable, then at least one variable or its negation in each clause, each of the k clauses, evaluates to true. Otherwise, it would not be satisfiable, right? Now, by construction, take the vertices corresponding to each true variable, right? Or its negation, okay? What can you say? What can you say about this set of vertices? Well, one thing that you can say is, how many clauses did you have? And you're taking one variable from each clause, or one vertex from each clause. Its size is going to be k. But also, are they going to be connected or not? Right? We argue that each pair is connected, thus forms a clique. All right? One, they are chosen from different clauses. That satisfies the first condition of the construction that we did. And two, what else can you say? They are not negations of each other. All right? In other words, like say x of I and x of I negation. Right? Why is that important? In the original clause, if they were negations of each other, right? For example, if I chose x2 here and x2 here, if those are my two choices of variables over here, could I come up with any assignment that would satisfy them both? No, because if I put this one at 1, this becomes 0. If I put this one at, if I put it at 0, then this is false and this is true over here, right? So both of those conditions give me the fact that, therefore, the vertices are connected. Right? And that holds for every pair. And if every pair is connected in this subset of vertices of size k, well, you've got yourself a clique by definition. Okay? So all you're doing is mapping a formula to a graph gadget. That's what we mean by gadget, right? This thing over here that I drew is a gadget, right? And I don't now now that I've clarified that a little bit in my head, see if I've got yeah, I've got another color here. What does this correspond to? Where's my original? Here we go. There's my original, and there's the. So I was choosing 0, 0, 1, and if I do that, which one is true over here? 0, 0. This one is 1, but also this one is 1. So either or, right? It would be either or in this first clause. And so you chose x3. That's fine there. This one would be 0, so that's not true. This one would be true. This one would be false. So actually, I would have to connect it to, for this particular one, I would have to connect it to x2 up here. But otherwise, I've chosen this one, and then if I do that over here, the only one that I can choose is going to be x3, and so that corresponds to that. And then, of course, I could connect those two. So that truth value assignment corresponds to the blue one here. Let's see what yours corresponds to. So if I choose x1 over here in the in C2, then that means I have to have 1, right? Because it has to be true in clause 2. If I choose x3 in clause over here, then that has to be true. And so oh wait, so that was in the first clause. So 1, 1. What about this last one? That's one. You said x2. That has to be true. So your choice, the red choice that you originally gave me, would actually correspond to this assignment instead. Right? This blue assignment is the one that I chose. But every satisfying assignment will correspond to some triangle over here. Right? Okay. So that's the idea there. You can. That's the mapping. We show we gave a high-level proof that it preserves the solutions, but now we need to do step 5. The mapping can be computed in polynomial time, right? And that's pretty easy because all you have to do is for each clause, Ci, for each variable, x sub I, or x of let's say ji in Ci, right? Output a new vertex v sub ij, right? That's pretty easy. What's that going to be? If there are k clauses, this is order k. How many variables are in each one? 3, right? So this in total is order k, which you can say is bounded by order n, right? Now that takes care of all the vertices. Now for each vertex pair, I'll relabel them as vi, vj, alpha, beta. Then apply the two conditions, right? If I is not equal to j and v sub alpha I is not the negation of v beta j, then add the edge v sub alpha I, v sub beta to j to E. There. And of course, what is this going to be? Well, if you've got 3k vertices, then this is 3k choose 2. That's going to be order n squared. Right? So, and it's all deterministic, right? Did I have a guess phase here at all? No. All I was doing was a mapping. Right? For each clause, output, for each variable in that clause, output a new vertex. For each vertex pair, of which there are order n squared at most, then just apply these two conditions and add an edge. And you've output a new graph. The input, of course, is going to be a formula. The output is a graph such that it has this connection between the two, that it preserves solutions. Okay? That was the last step. So therefore, really messy now. Therefore, 3CNF reduces to Clique. And that implies, because 3CNF is a known NP complete problem, that implies that Clique is NP complete. So it's one of those classes of problems that is extremely hard. And provably it is hard, or at least as hard as other seemingly difficult problems. Okay? Again, this is your landscape over here. Where's the landscape? There we go. This is your landscape. Oh, as you go up, that's why I don't like the term reduction. Reduction seems like you're reducing it, you're making it something less, but actually you are mapping it to a problem that is more complex. Down here, you can think of these as the easier problems, and these are the more difficult problems. But then I went ahead and crossed out more because technically you can only say that it's at least as hard as. It is still possible, if P equals NP, that this entire landscape collapses down to just P. Right? We can't say that it is provably more complex. We can only say that it's at least as complex as everything down here. Okay? One more example, right? And this is a little bit more fun example because the reduction is even simpler. What we're going to do is we're going to show that vertex cover is NP complete. Right? So what's a vertex cover? A vertex cover is given a graph, G equals V comma E. We want to find a subset of vertices, V prime of V, that covers every edge by at least one endpoint. All right. So let's look at a graph here. There. There, that's good. All right. Here's a vertex cover. Take all the vertices, right? Then, of course, that's always a solution, right? What we actually want to do is find the minimum vertex cover. And by a cover, we mean, here's one possibility. Let me go ahead and get my pencil so I can erase. There we go. Go ahead and select this one. If you select this one, then that covers this edge, it covers this edge, and it covers this edge. But this edge over here is not covered, nor is this, nor is this, nor is this. So continue selecting. Okay, well, I need to cover this edge. Hey, if I select this one, I cover both this edge and this edge. Okay. But this edge is still not covered, and this edge is still not covered, so I'll go ahead and select this one to cover this edge. And, well, I have to cover this edge, so I could select this one or this one. I'll go ahead and select this one. There's a vertex cover of size 4. Okay? Can you do better? Okay, what? And I'll trust that you're giving me the optimal one here because I'm going to use it in pen, so I can't erase it. What?
Instead of picking the bottom right one and the top left one, you just pick the bottom left one.
All right, that covers this, this, and this. I still have some other things that are uncovered, though. So what?
Then you could pick the same one that you did for the first one.
This one right here?
Yeah.
Okay.
And then the rightmost one.
Okay. I could have probably chosen this one and then this one too, right? And that would have been a vertex cover of size 3. There are multiple possible optimal solutions, right? But there's a vertex cover of size 3, right? So how do we go? Brute force, of course, select every single subset, starting with the smaller subsets first and working up until you find one of size k. Right? That's brute force. How many possible subsets are there, though? If you do this brute force, it's going to be order 2 to the n, because there are 2 to the n possible subsets of the vertex set of size n. Okay? So this is a very difficult problem, and we're going to prove that it's a very difficult problem. We're going to show that the clique problem reduces down to vertex cover. So in some sense, this is an even easier reduction, because we're not transforming like we did with 3CNF. We took a formula and we translated it to some completely different other object. What we're going to do is we're going to reduce a graph to another graph. Right? In fact, it's going to be the same graph. Right? Well, kind of the same graph. Okay. Virtually the same graph. Okay. So here is my reduction. Oops. Yeah. Okay. Okay. I don't have it as 1, 2, 3 in the notes, so I'll go ahead and go with 1, 2, 3 here. 1, we're about to show that vertex cover is in NP. All right? So all we have to do is come up with a non-deterministic polynomial time algorithm that decides it, right? That accepts it or rejects it. So guess, here's my guessing phase, a subset V of size k. Right? So we're going to do the decision version, vertex cover of size k. Right? We're not going to do the optimization version, because remember, you can always take an optimization version and transform it into a decision version simply by encoding k along with your question. You don't ask, what's the best vertex cover that there is? What's the smallest vertex cover there is? You simply ask, is there a vertex cover of size 2? Is there a vertex cover of size 1? Is there a vertex cover of size 3? Yes. Okay. Then that's your best vertex cover. Okay? So guess a subset of size k. This is going to be, of course, order k, which is order n, right? Because any subset of size v is going to be bounded by n. Then verify. Verify your certificate. We need to see if this is a vertex cover. So all we need to do is, for each edge, E in E, we'll say that E is, the endpoints are x and y. If x is in the vertex cover that you guessed, or y is in the vertex cover that you guessed, then it's covered. So if that's not the case, then we know that that's not a valid vertex cover, and we can reject. Right? I wrote it like this because that's the way that I spoke it. Of course, how could you translate this? What could you do this negation? Bring it in. X is the first endpoint is not in your vertex cover, and right, the second endpoint is not in your vertex cover. Right? What law was this called? I've been asking 235 stuff, hoping that you remember it. What is it called? When you distribute a negation? Yeah, there you go. I was about to say, remember your rums, all right? De Morgans, right? No, that's not that. What is the actual rum? Captain Morgan, right? Yeah, there you go. All right. Terrible rum, though. All right. So you reject it. Otherwise, if there's one edge that's not covered, then you reject it. Otherwise, you accept. All right. Always go blonde on rums. All right. Does Captain Morgan make a blonde? Anybody know? Okay, I don't know. I'm sure that they do. All right. So that was so B. Or part 2 is we're going to choose a known NP complete problem to reduce from. Well, I already did that for you, right? I said that we were going to reduce clique to vertex cover. Right? 3, we come up with a mapping. Okay? Now to do this, I'm going to draw you a picture instead. Okay? I'm going to draw you a picture of a graph, and we're going to look for a clique. Okay? So here's A, B, C, D, doesn't matter what the labels are, E, F, and G. There we go. And I'll draw a graph like this. All right. Now, does there exist a clique of size, say, 4? Say that K is equal to 4. N here is obviously 7, but that has no bearing on the problem. I'm looking for a clique of size 4. Is there a clique of size 4 here? Yes, where? This set right here. Okay. Now what I'm going to do is, now that has, there's might be a vertex cover here or not. That's not what the mapping that I want. So the question up here is, does there exist a clique of size 4? What I'm going to do is I'm going to transform this into a slightly different graph. A, B, C, D, E, F, G. Okay? And 1, 2, 3, 4. B will be connected to F and G. D will be connected to G and F. C will be connected to G, and it's already connected to A. And E will be connected to F. I think I got them all. What graph did I just draw? If this is G, what was I doing? I looked at A and I said A is connected to B and A is connected to D. So I won't connect them over here. A is not connected to C, E, F, and G, so I will connect them all over here. What graph is this? It's the complement graph, right? Exactly. And so some authors use the prime symbol here. Some authors use the overline symbol. I kind of prefer the overline symbol because that's a negation. So it's like taking the adjacency matrix and negating everything. If it was 0 before, it's 1 now. If it was 1 before, it's 0 now. You're basically saying if there was an edge, then now there's no edge. If there wasn't an edge, B to F, now there is an edge. Okay? Now I'm going to ask, is there a vertex cover of size blank? Okay? So the hint that I'm going to give you is think about the opposite, right? This is this is the opposite graph if you want to think of it that way. This is the graph, this is the complement graph. If this is a clique of size 4, then what is the opposite set over here? And there we go. All right. Take those 3 vertices over here. What do? A will cover all of these edges. G will cover this edge. F will cover this edge. Am I missing anything? Well, going over to B here, that edge, going from F to A, or F to D, excuse me, the F covers that edge, right? All of these edges have been covered, and this edge and this edge have been covered. Guess what we have here? We have a vertex cover of what size? 1, 2, 3. Right? What are the relationships between these things? If there was a vertex cover of size K up here, in the complement graph, there's going to be a vertex cover of what size? Not necessarily close. Up here, how many elements did I have? 7. Down here, and then there were 4 in there. How many are left over? And minus K. Right? That's going to be in the other set. Right? So our mapping will be inspired by this. The mapping will be taking a graph G and an integer k, and we're going to map it to G complement and n minus k. And you know how to take G complement. You just flip all the edges. Right? And of course, you can do this. Everybody can do subtraction. Right? Such that G has a clique of size k if and only if G complement has a vertex cover of size n minus k. Okay? That's my claim. Step 4, we need to prove it. ... I'll come back to that. Let's take care of step 5 because it's super easy. How do I show that this mapping here is polynomial? Right? For each pair of vertices, x, y, in V, right? We will let G complement be a graph with the same vertex set and then an empty set for the edge set. For each pair of vertices, if x, y is an edge, then we won't do anything. If it's not an edge, we'll go ahead and add x, y to G complement. Right? So this is clearly going to be order n squared for whatever you're doing. If it's an adjacency list, adjacency matrix. If it's a matrix, just go through and flip all the ones to zeros and zeros to ones, and you're done, except ignoring the diagonal. Right? And then I'll also, of course, output G complement and n minus k as your mapping. This can be done in order 1 because it's just a subtraction. Okay? Now let's come back to this claim here, and that's what we're actually going to prove. Okay? Where is it? Here, this is what I want. And I really like this proof because, and hopefully I forgot to review it, but hopefully I remember it in time because I think that it's an excellent application of the contrapositive. Let's make sure that we remember the contrapositive. What is the contrapositive? P implies Q. What's the contrapositive? Not Q implies not P. There you go. Okay? You can show that these are equivalent. Right. All right, so here, again, our claim. So we're going to prove it one way. Right? We're going to show that if G has a clique of size k, then, this is P, right? Then G complement has a vertex cover of size n minus k. That's the one direction, then we'll go the other direction, okay? So let C be a clique of size k in G, okay? Furthermore, let, of course, C be of size k, and so let E, U comma V, be an edge in G complement. We need to show that E is covered by some vertex in the vertex V minus C, right? Remember, we're looking at the other, right? So if this is C, then V minus C gives me the other vertices in this graph here, okay? So all I'm going to do is I'm going to follow the definitions. That this is an edge in G complement. Well, this implies that it's not an edge in G, right? So the E complement here, if you want to look at it that way. Well, that means that it is an edge in the original graph, right? This implies that U is not in the is U is not in the clique? I'm going to confuse myself. Oh, sorry. What did I mean? Okay, there we go. U or V is not in the clique. Okay, there we go. I just confused myself because I forgot to cross this out. So UV is going to be an edge in G complement. That means it's not an edge in the original graph. If it's not an edge in the original graph, then that cannot be in the clique, right? So therefore, either one of its endpoints, or both, right? One of its endpoints is not in the clique, right? It's not because they're not connected. U and V, are not connected in G. Right? So therefore, it cannot be part. One of these could be in the clique, the other could be in the clique, but at least one of them is not in the clique because there's no edge here. Okay. So this implies, again, we'll go back to the other one, that U is in V minus C, and all I'm doing, or V is in V minus C, right? Which implies that UV is covered by either U or V, or both. There we go. And the visualization looks something like this, right? In G, if it's not an edge here, then it's definitely an edge over here, and therefore it's covered by one of the by this edge outside. Okay. Now the other way is the application of the contrapositive. So remember, we need to prove an if and only if condition, and you can do that by either showing that that yes instances map to yes instances and no instances map to no instances, or you could do it so that yes instances map to yes instances and the yes instances over here map to instances over here, and that's what I'm going to be doing here. Let C, a subset of V, be a vertex cover of size n minus k in G complement. Right? And observe, what does this mean? What is the definition of this? For all U and V in the vertex set, UV is an edge in this graph implies that U is in C or V is in C. There you go. Nice compact 235 way of doing this, right? Let's go ahead and parse this out in English. For every pair of vertices, U and V, if U and V are connected in G complement, right? This is the complement edge set in G and V and edge complement. If they're connected, then because C is a vertex cover, either U is in C or V is in C, because this edge has to be covered, right? Here's U and here's V, and they're connected. So to cover this edge, either this one has to be in the vertex cover, or this one has to be in the vertex cover, or both. But that's covered by this right here, right? True or true is still true, so that's okay. All right. Now, what's the contrapositive of this? Well, the contrapositive has no bearing on the universal quantification here. But what's the contrapositive here? This is P, and this is Q. P implies Q. So go ahead and negate this. What happens when you negate this? Remember De Morgan's law. right? Just think rum, right? U is in C. What happens to that when I negate that? U is not in C, right? And V is not in C. Okay, that's negation of Q. Implies now P. What does this say about P? U comma V is not an edge in E complement, but I've got a double negation. What do I do with a double negation? Not an edge in E complement. How could I rewrite this? It is an edge in E, right? So, if I've got U and V, they are not in this vertex cover. I'll label it as VC, U and V. In E, this is G complement over here, right? If both of them are not in in this vertex cover, then in G over here, U and V must be connected. So if you take everything outside of this vertex cover, in other words, V minus C, forms, everything will be connected outside here. Everything is connected, highly connected. So V without C forms a clique. How big is it? Well, the size of V is n. We said that the size of the vertex cover here is going to be n minus k. Minus k. Therefore, if I start with n and I subtract everything outside of it, then I get k. It forms a clique of size k. Right? And all you had to do is take the contrapositive. In fact, you might be able to get away with one proof here with just this contrapositive. Yeah, I think you can do it. You don't need that part of the proof then, but I include it in the lecture notes too. Right? So that effectively concludes everything in the course. Hopefully you'll